There'll be many still continuing our discussion on how to use PDFGUI, which is about the filling the PDF data. So last lecture, we were focusing on doing the calibration using the NICO standard, right? So if you still remember the procedure, what we do is we input the GR file of the NICO, and we fit the NICO standard, the data against the NICO structure, which is very simple FCC structure. The purpose is to obtain two parameters. One is QDamp, and the other is a QBroad. So if you still remember the details, the QDamp and QBroad, they have a large contribution from the instrument, but they actually also have some contribution from the sample. But once we can obtain those values, we have a very good starting point to begin with. So we can write down those numbers that obtained from fitting the NICO data and use those numbers as a starting point for fitting the real sample data. And the real sample we're talking about is titanium sulfide. So last lecture, we discussed the structure of titanium sulfide. It's actually more like an O1 structure, and it has the HCP stacking, and the structure is very simple, only one degree of freedom in terms of their atomic position. Oh, by the way, Shar, are you recording the lecture?
Oh, yes, I'm recording it.
Okay, good. Yeah, because I think Karen mentioned that she might want to look at the video. Okay, so what we do is we start the new fit, and you can open your own software and follow my steps. And then we input the data set. So remember, there's our titanium sulfide pristine GR data. This is the process data. So if you still remember how we process the GR data, we start with the Fit2D, right? We obtain the two-column diffraction data from the raw imaging in Fit2D software. Then we subtract the background, and then we do the Fourier transform in the PDFGUI. So I think I sent you the comment for doing such kind of a Fourier transform. So you input the data and background and ask the software to do the Fourier transform, then you get this kind of GR data, which is the data in the R space. So we input this GR data. And before we do anything about it, we can actually take a look how the data looks. Can you guys see the plotted figure?
Yes.
Yes.
Okay, good. So yeah, this is the GR data plotted in PDFGUI. So you can see the typical oscillation features of the PDF data. And in fact, you can see the intensity of those peaks has a general decaying behavior as you go to the higher R. So I explained this in the last lecture. This relates to the QDamp. It's has origin both in the instrument and also in the sample itself. So for the instrument, because we have limited the angle resolution, and what that means in terms of the R space is actually the signal will decay as we go to the higher R. And also the sample might have a limited crystalline size or limited coherent scattering domain. So the sample can also contribute to a weakened signal at the higher region. So this is how the data looks like. Now we have input the data, and we can see some of the details here. So this means we are using the X-ray data. If you are inputting the neutron, remember to select the neutron. Sometimes a neutron is not by default. So remember to tell the software what kind of a radiation source you use, because neutron and X-ray have a very different, the scattering factor, and the patterns are computed in a very different ways. And this is all by default. We can just leave them there. And this is data range that is intrinsic to your data itself. And this is the fitting range. So fitting range is telling the software what range you want to do the fitting. So you can change this range. Sometimes you do this purposely, because sometimes the local structure can be different from the average structure. And this is typical in some complicated structures. For example, and this enriched material, if you happen to have experience with this enriched, actually the structure is quite complicated, and the local structure is very different from the average one. And even for some seemingly simple structure like AMC, right, it's based on the less structure, it's in fact is also complicated. So that is particularly more obvious if you measure the neutron data, and if you try to fit the different ranges, you will see that you can obtain some very nice fitting at the high region. For example, let's say from fit range from 10 to 30, some kind of a longer range. But if you fit from, let's say, from 1.2 to like 10 angstrom, then you will not be able to get a nice fitting just using the average structure, because the real structure is actually more complicated than what people usually think. And so this is something you can do. And so in fact, to check if there's local complexities, right? You can you can set this range to some small number. This is just around the beginning of the first peak. First peaks typically around the 2 angstrom something. So you can set about 1.2 to 10 something. So this is a very local region, and you can check if you can really fit the data well using the average structure. If you can do that, that means your structure is in fact relatively simple. So local structure have no abnormalities. Otherwise, you can start examining what could cause the complexities. For example, there are local features like including the local ordering, and there's maybe Rantello distortion. Yeah, all those local complications can make actually the average structure inappropriate for fitting the small range. Okay. And the scale factor is basically just a linear coefficient that put in front of the intensities you get. So this is very trivial. And Qmax is this is actually the parameter that was used during the Fourier transform. So if you remember, in our Fit2D data processing lecture, we talked about actually the Qmax that relates to the edges of the 2D image frame, and so normally about the 22 is a good number for Qmax. It's good enough for most of the data will be processing, and there's no point going to a very high Q, because at XPD you will not be able to get those data on edges, and so which means you cannot really access very high Qmax. Let's say 26 something. 24 is about actually the maximum you can get at XPD. So yeah, do not have to be too greedy about this number, and this number do not need to change. It's actually some recorded number during the Fourier transform. It simply shows here. And this is Qdam, the parameter we mentioned last time. So this both Qdam and Qbroad are the parameters we obtained from nickel standard fitting. So if you still remember, this number was about 0.03, and I think this was about 0.02 something. So you can input those numbers as a starting point, and you can also be more exact by looking at the fitted results of them and put them here. And the temperature and doping, this is something I think we mentioned the last time. It's simply a label telling the software what the temperature and what doping level those samples are related with. It has nothing to do with the fitting process, but it can be used at the final stage when you plot some of the parameters as a function of the temperature or as a function of doping levels. It's better when you have a series of data fitted, and for example, you want to see how the bond lengths change as a function of temperature. Then there's some convenient way to cite them. You can plot here, and you can choose the x as, for example, as the bond length or as some specific parameter, and I'm sorry, x as the temperature. So I think it's not shown here because we did only one data fitting. If you do multiple data, there will be a temperature showing here. So you can select x as temperature and y as some specific physical parameters and see how the trend changes. And the same thing is true for the doping. Okay, so this is the data. After the data, we input the phase. Let's open it. So, okay, we have the titanium sulfide phase. It's already there. Okay, so this is lattice parameter. Well, we discussed last time, and this is a hexagonal lattice. Have this kind of alpha beta equals to 90 degrees with gamma equals to 120 degrees. And this section relates to some of the parameters we'll be using for the fitting. So this is scale factor is simply also a coefficient before the intensity. So you may ask why there's another scale factor. We have already had one scale factor. This scale factor is more like actually a global parameter. So what this means is, let's say you have a multiple phase to fit, and you have this data, but this sample contains, let's say, two phases, right? Maybe one is titanium sulfide, the other turn out to be, let's say, lithium carbonate or nickel oxide. So whatever the phase, there are multiple phases, and this parameter actually applies to all of them. And in each specific phase, we also have a scale parameter that only applies to this phase. So I don't know if we have time or actually to discuss about the multiple phase fitting, but and that would be a good case to show how we sometimes can play with this parameter to get some good starting point. So you can have some rough estimation of the each phase fraction and input the numbers here. And that will give you a starting point for their multiple phase fitting. Okay, and delta 1 and delta 2, probably we also mentioned this last time. This relates to the abnormally sharpened the first peak in the PDF. So because in the lower range, actually the atoms, they are correlated. So this bond and the other bond actually, they have correlations. What that means, that would make the typically the low R peak, usually only in the first peak, much more sharp than their other peaks. So these two parameters account for this kind of a unique sharpness. And depending on the relationship of correlation, so if you put the cursor here, you see that there already some explanation for this. So this is a linear atomic correlation, and this is a quadratic. And so you can refer to the PDFGUI manual to see their mathematical definition. And you can also choose which one you want to use. You just use one, do not use two. Yeah, either use this one or this one, and use them for fitting the lower peak. As a rough estimation, what I normally use, I use delta 2, and delta 2 typically has a value around 2 angstrom if you have the first peak around the 2 angstrom. And if this metal, let's say it's pure nickel or pure iron something, then something higher. So it has on the same scale as the first bond, as the shortest bond length, and with the very likely number of being 1 or 2 something. You can start with 1 or 2. That's good enough. And this is also a parameter, um, um, could be useful when you fit in the nanoparticles. If you have nanoparticles that are, say, around 30 or 40 nanometers, you can define this parameter, which is basically telling the software the coherent domain you are expecting. And this number can also be fitted. And this is also another, actually, the parameter accounts for the lower sharpening, but is not very often used. And if you really want to know the details, you can also check the menu there. So this is our card is basically also relates to the peak sharpening. These two parameters are much less frequently used than these two. So normally, I think it's not very necessary to really get involved into these two, but if you insist, you can check the menu and seek the guidance on these two parameters. And for the step cut, so this is basically the cutoff and their value for their profile function. So as I mentioned, actually there's a profile function which relates to the instrument. So this parameter is telling the software there where to cut off. It's some kind of at the meaning of the window. So to simulate the profile function for the PDF. And let's continue. And so here it says included pairs, and now it is all to all, right? So which means that we will compute the PDF histogram of PDF data using all the atomic pairs, which is exactly what we do in the measurement, right? So in the measurement, actually, the PDF data considers all the atomic pairs. So this is saying that we will compute the PDF data based on this structure using all the atomic pairs. But we can play with this. So I don't know if you can see this kind of a menu that is actually hanging around, or the cursor. So you put the cursor here, there will be a sub-menu hanging around, suggesting that you can change them, right? For example, you can change to titanium. And what this means, the software will still use this structure, but it will disregard all the other atomic pairs. For example, titanium sulfur will be not considered. Sulfur will be not be considered. It will only show the pattern relates to the titanium. And this function can be very useful if we are particularly interested about some specific atomic pairs. If time allows, we will show how to use this function, especially for neutron PDF data. And we'll discuss why we do the neutron and why neutron can be so effective in characterizing the oxygen-related structures. So at this stage, we'll stick to all. Okay. And this is basically the structural parameters. We can tell it's listing all the atoms in one unit cell. So if you still remember the titanium sulfide structure we covered last time, we plotted that structure in Vesta software, and we went through the structural information about this phase. If you still remember, this sulfur occupies a 2A or 2B Wyckoff site. That means there should be 2 sulfur atoms in one unit cell, and titanium occupies 1A, right? And I think we mentioned is 1A because you see the atomic position is so special. It's at the intersection of all the symmetry elements. So there's only 1 titanium atom in the unit cell and 2 sulfur atoms. And in terms of atomic positions, this is also very simple. So you see, this is a unique number. This is basically 1/3. This is 2/3. And this is some number very close to the 0.25, right? but it's not the exact 0.25. And this is number is something needs to be determined in order to really finalize the whole structure. So there's only one freedom in atomic position, which is this Z value of the sulfur. Also, this is U values we covered last time. Just a little bit recap that this relates to the disorder parameters. So in XRE, it's basically dampening the intensity, especially at high angles. So in PDF, it contributes a broadening of the peaks. So if you, let's say, if you put them at 0, you will see a very sharp PDF peak, which is not real, right? Because they have some values, so you typically see the PDFs peaks have some kind of width. Once they are the same, and the disorder term is termed as their isotropic atomic displacement, and that's what we usually do, right, for this kind of simple structures. But surely we usually set to those values based on their sites. So this site is based on the titanium. It's a transition metal, so typically you may have a UISO value around 0.05. So this is a good number to start with. For sulfur, it's a lighter elements, so the value might be slightly higher. Let's say 0.08. This is just some number to guess. And we do not consider any anisotropic disorder, so we just assume as a 0. And same is true for U13 and U23. And OCC stands for occupation, and we assume they're fully occupied. So this is the structure we have. Okay, now we input everything we need into the software, and we can start think about what parameters we want to define, right? In fact, in the process of fitting the NICO standard, I already mentioned some of the strategies. Since this is basically based on their linear progression, so actually, the starting point is important, because that relates to whether you can really find the global minimum. And when we talk about actually this the landscape of those this fitted parameters, and also how the fitness improves is dependent on those parameters in different ways. So if you remember, I would strongly suggest you always start with a scale factor, because this is simply a coefficient, right? So it will not cause any stability issue related to the fitting. But if you start with, let's say you start with this delta 2, then chances are you may run into problems during the fitting. You may see your fitting stuck at some stage, or your fitting cannot converge, because this parameter relates to the fitting in a more complicated way. It's not simply a linearity. It's not a linear relationship. So what that means, if you vary them in a way that is not predictable, actually the software may even have the chance of getting crashed. Yeah, or it cannot, the fitting cannot converge. So we start with the easy ones. The easy ones are scale factor, the number one easy parameter to start with. Number 2 would be the lattice parameters. They are not exactly linear as the scale factor, but they're very easy to deal with. So scale factor should be the second batch of parameters to deal with. And continue with the lattice parameters, then we go on to normally to the UISO values. So those values, they are more complicated than lattice parameter, but they're relatively stable for the fitting. So that's why I think I also mentioned, that's why I have this habit of naming these parameters as 2 digits. So for example, normally I use this as the like 100, and this is like 1, 2, This is 1, 1, 2, and this is something like 11, right? The 2 digits, same number, or we have another UISO, then 22. If you have a third one, then it will be 33. This is my personal habits, but it helps myself to actually keep in mind the sequence of fitting and also the physical meaning of those parameters. And the next one I will be looking at actually atomic position. And so for atomic position, I probably would choose 3 digits, something like, let's say, 111 or 110, something, just to keep yourself reminded that those relates to the atomic positions. And those parameters are typically the parameters I refine last. And though I refine this last, maybe together with the actually atomic position, depending if the fitting is stable or not. And also remember, we still need to refine those 2 parameters. Even though actually they have the initial value obtained from their nickel fitting, but still they need to be more accurate to really describe the specific PDF data of the sample. Okay, so let's get started. Remember, this is the first parameter we want to refine, right? We define it as 1, and this is 2. Remember, we do not need to do anything about those angles, since this is a trigonal symmetry, hexagonal unit cell, so the angles are fixed. We do not need to do anything about it. Also, I mentioned the scale factor, and this is where, in fact, this is the first one to start with, but just a kind of a personal habit, I normally name it this 100 parameter. And we only need to do one, right? We have this local scale factor. We also have the global one. We only need to define one. So I already would define this one. Okay, and we'll leave either this one later, and we start defining their U values. We can start with their titanium because it's heavy. So actually, any change in titanium would have a more obvious influence on the PDF data than the sulfur. Yeah, so titanium and the PDF data is more sensitive to the movement of titanium. So let's define it as 11. Since it's isotropic, we define them as the same. And these two would define as 22, right? And here, so this is the place you may want to make a little bit note, is that how we define atomic positions in the PDFGUI. What we usually do is actually we simply select all the atomic positions and we right-click symmetry constraints. So what this means is actually confirming this structure, even though it looks like a simply listing all the atomic positions, but it has intrinsic symmetry with this kind of a specified space group, which is a P3 bar M1. And also, depending on how you define this structure, because for some structures, there are 2 sets of origins. So sometimes there's a 000 is one set. Actually, there's also another shift, like a quarter, and a quarter. So that's a different set of origin, which is sometimes also used depending on your motivation. At some point, we'll discuss more about how to choose the different types of origins. But for this time, we just to keep this simple. We just leave it as default. This is simply 0, 0, 0, right? And this is checked constrained positions, meaning that when we refine all these positions, we still apply this kind of a symmetry constraints on them. So they cannot vary in a very random way, but they should be varied actually under the constraint of their space group symmetry. So that's what is mean here. And we can uncheck this one. So what this means that, remember the disorder factor of the atomic displacement is actually also related to the symmetry. So if you want to really refine the anisotropic atomic displacement, for example, you want to refine U13, U23, then you also check this one. But in this case, since it's isotropic, so we just uncheck it and OK. And now you see the software will actually automatically defines this position as the 111 parameter. And this position is related to that one by this kind of a translation. So it's basically, it's like a mirror, right? It's apply a mirror first. Since x, y the same, and there's a mirror such that z is actually the opposite. Then there's a unit cell along one of the unit lengths translation. So that's why there's a +1. So this software and this software, they are related by symmetry. So we only need to define the position of this software, then automatically the position of this software is defined by the symmetry. And this is more useful when you have a more complicated atoms list. For example, you may have a 10 or 20 atom list. Then if you apply this kind of a symmetry constraint atomic position fitting, it will automatically define the minimum number of atomic positions with other atomic positions related by their symmetry actually will automatically follow this defined parameter. So basically, we have already finished the definition of the fitted parameters in this panel. Sorry. And let's move to this histogram. We have this two that needs to be defined. So let's say, oh, I'm sorry. And let's go back to this one. We have this delta 2 not defined. So let's put it to 200. And just to remind ourselves that this is this needs to be refined at a later stage. So you see, generally to follow the value of the number follow the sequence of the fitting, right? So okay. Now let's go to the histogram. We'll click on the constraints panel. Define this as something like 301, meaning that these two parameters will be refined last. Okay, and remember, you save your fitting with some file names that's easy to remember. Okay, then we go to the fit, right? And make sure we have everything defined here. Just one last check. Okay, so let's get started. Okay, oh, this is up to 10. We want to do something maybe even to higher R. Okay, and you see there's some Fourier transform ripples at very low R, right? Somewhere here. This is not due to the bonds. This is purely caused by the Fourier transform, since we have limited the Q max. So we might as well start from, let's say, 1.9 something, right? This should be the first peak, the first bond. We can start from here, 1.9 something. Okay. Okay, now it looks good, and we start doing the fitting. We can first get everything fixed. Then we can easily choose the parameters we want to do the fitting, right? Remember, we started with a scale factor. This 100 is reserved for the scale factor since it's simply a coefficient, very easy to use. At the same time, I would say we can also uncheck this lattice parameters. So if you remember, this is a lattice parameter for A and B, and this is lattice parameter for C. So we can uncheck this three. and start the refinement. Oops, I think I forgot to close one of them. This should be closed. Yeah, this is what we just got. And I don't know if you also get something similar. You probably can reach our RW value around 0.2 just with one fit, right? Because the parameters we input are reasonable. So that's why you have actually a nice beginning. But you may feel there's too much gap between the observed fitted and the difference. You can change it. So let's say you can change this number, let's say 0.2. Oops, sorry. And you plot again, right? So now it looks closer. Close this one. So this is just with one run of our fitting, and we can definitely do better. So remember, our next step is to refine the UISO, atomic position parameters. They are general nice to deal with. You can be more cautious. For example, you can first just fit the heavy atoms, which is 1,1 for titanium, right? And if that one goes well, then you goes to the next step of fitting the sulfur. But here, because I know actually they are all good, and we can simply uncheck both of them and fitting titanium and sulfur simultaneously. And do this one, do the fitting. So you can visually see the improvement of this fitting, right? And also, I think you can have some idea what is causing the problem, because the long R range, as I would say, has already been nicely fitted, right? But apparently this one is causing the problem. And remember, this is the first peak, and it has a unique sharpness that has to be accounted by the atomic correlation parameter, right? So that's delta 1 and delta 2, and we chose delta 2. So now it could be a place to actually to refine the delta 2 to actually have a better description of this first peak, right? And we can do that at the same time when we do the atomic position fitting. So we can uncheck them. Oh, by the way, we just copy the refine to the initial, since there now are better numbers to start with, right? And remember to click apply. So now those fitted parameters will be the initial values for the next round of fitting. We uncheck 111. This is the atomic position of sulfur, right? Only one freedom. And same time we uncheck, okay, I think this number is a little bit, we forgot to actually put a number for this one, right? This number should actually, I mentioned should be typically is around 2 something. So we can just input 2 here. This is for delta 2. And now we do the fitting. Okay, so you see that actually the effect is very obvious, right? It's now much better accounted for. I mean, the first peak. And in general, there's a lot of improvement. And already we are reaching our RW value of about 0.11, which is already a nice fitting there. But we can do even better. First, apply, and then uncheck this too. Okay, and do the fitting. Okay, so probably this is the best we can get. We can have all the parameters defined, and there's no obvious reason that we want to go further, because we do not really have a good justification for defining the other parameters, since there's no more complications about this material. And also, by the way, if you remember, I mentioned at the beginning, you can redefine the range you want to fit, right? That's actually the range from 1.9 to 30 is about the average structure range, right? If you want to focus on the local, you can define as 1.9 to 10 Armstrong, which is a kind of local region. And if you can test if this average structure is still good enough to actually describe the local structure. So we change this range and we replot. Okay, this is fitting, and let's see it again, see if the fitting still works. Oops, something. I think, let me fix this. You see, sometimes if you let go of all the free parameters, it's not stable, right? So that's why we want to fit sequentially instead of simultaneously. So we now fix these two parameters that was causing the problems, and see if a more stable fit can be obtained. Okay, so in fact, it can be generally nicely fitted using the average structure, right? The value increased a little bit, but I would say it's quite reasonable if we consider about the other statistics. So this is actually a reasonable number, saying that the average structure is adequate to describe actually this kind of a local structure, because it can fit to the local pattern quite well, right? So this is saying that the titanium sulfide does not really have any local structural complexity. It is just what it is. Anywhere you see, whether it's in the 10 Armstrong range or in the 30 Armstrong range, it's the same. But you can try this on other materials that you work on, and you probably will see something different. You probably will see actually this kind of fitting would deteriorate quite a bit if you just use the average structure. Okay, I think that's pretty much about the titanium sulfide fitting. And I just want to go quickly about the next step. And next one is what I mentioned. I want to show you, you can really take advantage of this function. So this is taking account of all the atomic pairs in the structure. But how about some specific atomic pairs? So let's say this is a titanium sulfide, right? So I want to see where this peak is from. So I see this peak, then I just wonder, what's its origin? Then we can check. We have some very easy ways to check. My first guess would be, okay, this looks like maybe titanium, right? Since in the sulfide or oxide, the first peak is a transition metal, oxygen or sulfur, and the second one is a transition metal. That's my first thought. So let's try it. If we put it, that's not working. What happened? Oops, sorry. I should put it here. Okay, press enter, and we run it. Oops, there's some, we just do it again, okay. What we do, we just fix those numbers, because we're not doing any fitting. We'll simply just check the contribution of from specific pairs. We do not fit anything. Let's do it again. Oops. Make sure we get those fitting data. Okay, now it comes back. Okay, and then we check the titanium. Okay, so this is what I want to show you. So you see, it's telling us titanium is only contributing a fraction of this peak. This is against what I thought in the beginning. So you see this peak actually has, let's say, maybe only a quarter of the intensity contributed by titanium. And you can also see the contribution of titanium to other peaks. It's kind of at a very a large R region, right? So you can tell this region mostly has little to do with titanium contribution. Then where's this peak is coming from? If it's not titanium, let's try sulfur. Okay, and we run again. Okay, now we see the secret, right? So this peak is in fact has a dominant, is dominantly contributed by sulfur and sulfur. So this probably is somewhere against our intuition, since we think sulfur is much lighter than titanium. So the contribution from sulfur should be small, but in fact it's contributing quite a bit to the second peak. And then we can reorganize our thought, and we may realize that, okay, even though sulfur is light, so in terms of X-ray scattering, is kind of light scatter, a small scatter, but there's so much sulfur in titanium sulfur system. Its abundance actually make the sulfur-sulfur bond contributes to quite a bit, to have a lot of contribution to the second peak, right? And also you see the origin of these two peaks. You see this peak and you want the west front. So this peak comes from sulfur. And this also comes from the sulfur, right? And we can do the same thing for titanium sulfur. And not surprisingly, we should expect the first peak should be accounted by the titanium sulfur, right? So you see, this is titanium sulfur. It's contributing to the first peak. It's solely contributed by titanium sulfur. So there's no other contributions, only titanium sulfur. And you also see this peak relates to titanium sulfur, right? And if you look at Manning PDF data or EXAFS data, you actually have some kind of a sense. This peak relates to the second transition metal ligand correlation. And you also see the contribution to this peak. So all these contributions can be very easily seen just to use this kind of a nice function in the PDFGUI. Okay, I want to switch gear a little bit, and I probably will just want to touch it. I'll close this window, and I'll discuss a little bit about the Neutron PDF. Can you see my screen?
Yes.
Okay, good. So this is a paper we previous published. So I think it's worthwhile for you to know we have been working for a while on the Neutron PDF. So Neutron PDF, I like this technique because it gives some very direct visualization of their oxygen bond. So why we care about oxygen? Because we are interested in the oxygen redox. And in studying the oxygen redox, there are a series of phenomena that we need to pay attention to. And one of them is actually the distance between oxygen and oxygen. Because in some cases, this may relate to the dimer formation or whether the oxygen is actually stabilized by in the form of localized hole. So many of these kind of issues relates to the oxygen bond. Then how we probe it? If we use X-ray, I don't know if I can move this a little bit. Right, so this is for neutron. If it's for X-ray, I think you can definitely imagine this is very small, cobalt is very large, oxygen is also small, right? But for neutron, oxygen has a very large scattering length. So that makes oxygen the dominant scatter in some systems. For example, in lithium carboxide, actually the oxygen is the dominant scatter. And here we can directly see the oxygen peak. And this one is actually the oxygen interlayer peak. And this one is actually the oxygen intralayer peak. And we see the intralayer oxygen correlation doesn't really change upon charging, but it's interlayer oxygen bond that has obvious decrease upon charging. The purpose is to show how we actually can visualize these things using the previous function I mentioned. So in the email I sent to you, and there was actually a DDP file, which is the PDFGUI file, and that has already I made, and that one contains the Neutron PDF data. So let me share the screen again. Can you see my screen? Good. Okay. I see there's the confirmation from Sharp. So this is actually a fitted Neutron PDF. So fitting has already been done because we do not want to spend extra time talking about the Neutron PDF fitting. If you're interested and if you will work on this in the future, you're welcome to discuss with me. We can go through the fitting, but it's basically following the same philosophy as we do for the X-ray PDF fitting, right? And we can look at this fitted data. So this is the fitted Neutron PDF data. It's also PDF, but just a Neutron. It's already fitted using the lithium carboxide the structure. So this is the fitted structure. So we see the local structure can also be well accounted for by the average structure, meaning that the lithium carboxide, there's no real local structure complexities. It's just everywhere can be accounted, can be described, but simply the lithium carboxide, the layer structure. So, but we can take advantage of this function. So make sure I have everything fitted. Okay, good. So remember, I mentioned oxygen is the dominant scatter, right, in this system. Then let's check what that means. We run it. Okay. Yeah, now you see what I mean, right? So you see the oxygen atomic pairs is actually contributing to most of the patterns. This is something you definitely would not be able to see in the X-ray, since oxygen is such a light scatter in X-ray. But in neutron, you see these 3 peaks. They have they're solely contributed by oxygen. And if we relate to the structure, we can tell this is actually the interlayer oxygen, and this is the intralayer oxygen. So that's what I showed when I'm presenting the previous Joule paper we published at the beginning of the year. So you see, this is really the strengths of using Neutron PDF to study oxygen-related structure feature. So you see, these 3 peaks, they're so easy to tell, right? And we can look at other things. Let's say, how about cobalt oxygen? What are their contributions? Let's run again. Okay, so you see where cobalt oxygen is contributing. It's contributing to the first peak, right? But you may wonder why there's a dip here. We'll come back to this later. So, but this one is contributed by the cobalt oxygen. And if you read the numbers, you see this is about the 1.9 angstrom. This is exactly the bond length of a cobalt and oxygen, right? And this peak, these 3 peaks have nothing to do with cobalt oxygen. And this peak has contribution from the cobalt, but you may wonder why the specific contribution from cobalt oxygen seems to be even larger or stronger than the merit data. That is because this part also has contribution from the lithium oxygen, and lithium has a negative scattering length, which means actually peak will go downwards. We'll look at what I mean by this. Let's check the lithium oxygen and run again. So this is what I mean. You see, lithium oxygen, because lithium is actually a negative and oxygen is positive in neutron. So that combination leads to a negative scattering. So lithium oxygen has this kind of a negative peak. You see this kind of dip here. And if you check the distance is about 2 angstrom, which is exactly the lithium oxygen bond length. So this dip belongs to lithium oxygen, and this dip actually is compensating some of the cobalt oxygen peak and leading to the overall peak intensity we observe here. And you can also see the other contributions from the lithium oxygen, right? And we can look at the cobalt contribution. In X-ray, this should be the dominant contribution, right? Since cobalt is so heavy, it has much larger scattering power than lithium oxygen. Cobalt correlation should dominate the X-ray PDF data. But let's check if that's the case for neutron PDF. So we see cobalt is basically doing almost nothing to the to neutron PDF. So I need to backward a little bit. As I said before, I said these peaks, they're solely contribute, but I think I should be a little bit more conservative. They have a small contribution from the cobalt, right? But you can see this contribution from cobalt is so small. It's actually not comparable with oxygen. So we can still reliably use these 3 peaks to analyze the oxygen correlation, and we do not have to really care too much about the cobalt correlation. Okay, so this is what I want to show you, that you can take advantage of this function to include specific pairs, such that you can see their contribution in the overall PDF histogram. Okay, so I think that's the end of today's lecture.